Hello everyone, I want to take a quick minute and talk a little bit about how to assign oxidation numbers without having to draw a Lewis dot structure every single time. Now, one way to do this is on your useful equations packet. At the bottom, there are a list of oxidation rules as shown here. And this can help speed up the process quite considerably. Now, the original rules for oxidation numbers still holds true, where we just assume the bonds are non-covalent, and a most electronegative element will get those electrons. But this kind of helps spell things out a little bit in a fast way without having to necessarily know what the Lewis dot structure is. So, to go through this, we have a couple items here. So if you ever have a single element and it's in its elemental form, such as sodium or O2 or Cl2 or N2, anything like that, then the oxidation number is simply going to be 0 for that element. If you have a single element, monoatomic, single atom, and it is an ion, meaning it has a charge, then the oxidation number is simply equal to the charge. And then the third rule, and this is kind of the big one, the sum of the oxidation number values for the atoms in a molecule or formula unit of a compound equals 0. The sum of the oxidation number values for atoms in a polyatomic ion equals the ion's charge. So basically, whatever the charge of your molecule is, that has to be equal to the sum of all the oxidation numbers for all the atoms added together. And then there's another kind of table down here that kind of goes in order of how you should be assigning these oxidation numbers for these polyatomics. And we'll go through that in a little bit as I do some quick examples to help illustrate what we're doing here. So for our first example, we're going to look at Cl2. Now, if we were to draw out the Lewis dot structure for Cl2, or chlorine gas, we draw our two chlorines, put a line in the middle, and then we'd fill up our dots for our electrons. And so we can do that relatively quickly. Just putting one dot on each side until it's filled up, and then start carrying them off. Alright, so if we're to do this with the Lewis dot structure, we need to assign which one is the most electronegative. In the case of two atoms that are the exact same and have everything else the same as far as what else they're attached to, such as the case in this instance, that bond would essentially be split in half. One electron will go with the chlorine on the left, the other electron will go with the chlorine on the right. So when we're actually looking at this one and we're trying to assign the oxidation number, they will each get one of that shared electron. So if we go ahead and pull up a periodic table, we can look at chlorine and see it's right over here. So it'd have 1, 2, 3, 4, 5, 6, 7 valence electrons. So I'm going to kind of do it with the way of using Lewis dot structures to begin with. So we'd have 7 valence electrons. We want to subtract out all of the unshared electrons, in this case 6, and the shared electrons. So the shared electrons in this case, we're saying each of them will get one of those shared electrons within that bond. So it'll just be one shared electron that it gets the rights to. Alright, so if we do 7 minus 6 plus 1, or 7 minus 7, we end up getting 0. So instead of having to always draw out the Lewis dot structures, we can just say, alright, well this obeys that first rule, and so the oxidation number needs to be 0. And so when we write down the oxidation number for chlorine, we'll just say this is 0. Now again, the oxidation numbers are the average for that element in that molecule. In both cases, both chlorines are 0. Alright, Alright, let's move on to another example. Alright, let's say we have fluorine minus, so F minus. Alright, this one falls under the rule for number 2. This is a monatomic ion, meaning there's only one element and it has a charge. In this case, the oxidation number needs to be equal to the charge. So if we just did this with the chart, we can say, alright, this is a -1 charge, so it must have an oxidation number of -1. And if we were to draw out the Lewis dot structure, we would say, alright, well, we have our F here, we have our 1, 2, 3, 4, 5, 6, 7 valence electrons, because of 1, 2, 3, 4, 5, 6, 7 valence electrons. But now we need to add on one more electron due to this charge. So then we'd add in one more. And so now we have our F minus monatomic ion, and it's going to have 8 electrons around it. So we followed that same formulation as earlier. We'd say, alright, well, it normally has 7. We're going to subtract out the 8 dots. There are 0 shared, and so this one is going to be equal to -1 charge. Alright, now we're going to do an example for the third case here, SO4 2 minus. And for this one, we can kind of go through our list of rules, because drawing out SO4 2 minus might be a little difficult for some. Essentially, you have sulfur in the middle and surrounded by 4 oxygens. So for this one, we're going to just go down our list of rules. We know that it is not a single element because it has 2, so both of these are excluded, so we have to do number 3. Number 3 says the sum of all the oxidation numbers needs to be equal to that of the ion's charge. In this case, we have a charge of 2 minus, or a -2 charge. So now we need to go through this list and determine what those oxidation numbers should be. So for all group 1 elements, it's going to be a +1. So everything in this first column here, with the exception of hydrogen, because hydrogen is kind of unique. But lithium and everything down, if that's in a molecule, that'll have a +1 oxidation number. Well, we don't have any of those, so we're going to move on to number 2. Alright, if we have anything in group 2A, or the second column, anything beryllium down, it's going to have a +2 oxidation number. We don't have any of those, so we're going to move on. Alright, for hydrogens. For hydrogens, shown right here, if it's combining with a nonmetal, so pretty much any of these guys, it's going to have a +1 oxidation number. If hydrogen is combining with any of the metals, then it's going to have a -1 oxidation state, and that's because of its electronegativity. As I mentioned previously, hydrogen has a very similar electronegativity to carbon, so it's going to behave in very similar fashion. But we don't have any hydrogens here, so we're going to move on to the next one. Alright, for fluorines, fluorine is going to always be -1, and the exception of it being F2 gas. So if it's ever bonded with fluorine, okay. That's like the one case. Alright, we don't have any fluorines here, so we can skip that to the next one. Alright, now we have oxygens. Alright, so if an oxygen's in a peroxide, it's a -1. Little note about peroxides is if you have a peroxide, that's simply some species bonded with an oxygen, then that oxygen is bonded with another oxygen, and then there are some other species. So R is just representative of anything else. The main thing with peroxides is you have this OO single bond. So if we were to look at, say, something like hydrogen peroxide, it's similar to what we were doing with our chlorines, in the sense that both these oxygens have equal weight to pull those shared electrons, so they each get 1. And because of that, the extra electron is essentially taken away. So in this case, we would just have the electrons from the hydrogen and only one of the electrons with that oxygen bond. And so that would end up giving us a -1 oxidation number. This is true for both those oxygens. All right. I will always warn you if on a quiz or an exam if you have a peroxide. So just keep that in mind, but this is what a peroxide is. Most of the time, it is going to be -2. So the only time it won't be is if it's bonded with fluorine. Oxygen's a very electronegative atom or element, so it's pretty much always going to be -2, unless it's in its elemental form or is bonded with another oxygen in a peroxide. All right, so keeping that in mind, we're going to go ahead and say that oxygen is a -2 oxidation number. All right, so now we're going to go to the next one. And for everything in group 7, so our halogens, so essentially chlorine and down, since we have a rule for fluorine, it's going to be -1 unless it's bonded with oxygen or a halogen that's a little bit higher on the periodic table. Well, sulfur doesn't qualify as that, so what you do for species that aren't designated by this table is you have to solve for them algebraically. And so what we're going to do is we're going to go ahead and say that our sulfur, we don't know what it is, so I'm going to represent that to be x, just some variable. Then what we can do is we can say, take the sum of all of our oxidation numbers and have that equal to our charge. So we're going to have x multiplied by 1, because we only have one sulfur. Then we're going to do the oxidation number of the oxygens. So we're going to add those together. And for our oxygens, as a -2 oxidation number, we're going to multiply that by our number of oxygens. So in this case, 4. And then that needs to be equal to our charge of -2. And so we can solve this algebra equation for x, and that'll help us figure out what we're doing. I'm going to go ahead and put some shapes on here to help y'all figure out where things are pulling from. So we have this 4 here. We have the oxidation number of -2. And then finally, we have our charge. And this is where that is coming from. All right. So we can go through and solve for x. We can do x times 1, which gives us x, plus -2 times 4, giving us -8, is equal to -2. So we can say x minus 8 is equal to -2. Then we can add 8 to both sides, and we can get x is equal to a +6. And so that is going to be our oxidation number for sulfur. And so now we can write down that sulfur is +6. And so that's how you can go through and find the oxidation number assignments for each element in a compound without having to know the Lewis dot structure. Thank you guys, and I hope to see you in the next video.